Modern physical engineering, from aerospace robotics to high-speed industrial machinery, presents immense mechanical complexity where the cost of failure is high. This creates a significant engineering dilemma. Testing a control algorithm directly on multi-million-dollar hardware carries a high probability of physical damage, often outweighing any benefit from early life testing. We are dealing with dynamic systems. By definition, these are systems where the variables change over time. The system's current rate of change depends on the values of the system variables at that specific instant. To navigate the risks of live testing, engineers rely on virtual prototyping. We translate the physical system into a set of mathematical equations derived from physical conservation laws, such as Newton's laws of motion. Constructing a precise mathematical model allows us to predict and analyze dynamic behavior mathematically before the actual machine ever moves.
A mathematical model functions like a map. It provides the specific features required for navigation without attempting to duplicate the physical territory itself. A good model is a deliberate simplification. It ignores physical details that do not affect motion, like the color of a component, to focus on the dynamic relationships required for control design. The process follows a chronological cycle. We establish the physical laws governing the interconnections, derive the mathematical equations, simulate responses, and analyze the resulting performance. This theoretical modeling from physics differs from system identification. System identification reverse engineers a model entirely from measured experimental input-output data. Ultimately, your ability to predict future events and safely design a control scheme depends on the accuracy and appropriate simplicity of this mathematical map. When modeling mechanical systems, our derivations are anchored in physical conservation laws, specifically Newton's laws of motion. Engineers translate these physics into one of four standardized mathematical architectures: the configuration form, the state space representation, the input-output equation, or the transfer function. The configuration form acts as our standard baseline. It is a second-order matrix format that organizes the system into distinct mass, damping, and stiffness matrices. Selecting the correct mathematical architecture is a foundational step. It dictates how a computer solver will process the system's cause and effect relationships. Regardless of a mechanical system's complexity, its dynamics can be deconstructed into three foundational, interacting physical elements. Consider a car striking a deep pothole. The resulting motion is dictated by how the suspension components manage that sudden energy transfer. The first element is mass, or inertia. This is the kinetic energy storage component, governed by Newton's second law for both translational and rotational acceleration. The second element is the spring. This is the potential energy storage component. It provides a restoring force proportional to its physical displacement. The third element is the damper. This is the energy dissipation component, providing viscous friction that scales with the velocity of the movement. Understanding a mechanical system's behavior requires mapping how these three specific elements interact, physically couple, and trade energy over time. To map these interactions, we must first determine the system's degrees of freedom. This is the specific number of independent generalized coordinates required to completely describe the physical configuration of the system. We will run a derivation on a 2-degree of freedom system, featuring both translational and rotational motion. This schematic shows our primary component, a cart of mass m sliding horizontally, constrained by spring K. Attached is a secondary component, a pendulum of mass m suspended by rod L, free to rotate by angle theta. Because the pendulum's rotational swing exerts reaction forces that impact the horizontal slide of the cart, their physical motions are mathematically coupled. Untangling them requires a systematic Newtonian derivation. The first step of this derivation requires us to isolate each body visually. This allows us to analyze the forces acting on each mass independently. This diagram isolates the green cart block. On the left is the free body diagram, showing physical forces, and on the right, the kinetic diagram, showing inertial forces. We map the external and reactive forces acting on the cart: upward spring force, Kx, downward gravity, mg, normal force, n, and joint reaction forces, v and h. Moving down the diagram, we isolate the pendulum, mapping its inertial forces,
identifying gravity pulling down, alongside the combined kinetic vectors for rotational and translational acceleration. By applying Newton's second law, sum of forces equals mass times acceleration, we equate the physical forces on the left to the kinetic forces on the right. This yields the algebraic equations of motion. The free body diagram serves as the primary bridge that translates physical geometry into the differential equations used for analysis. The equations of motion are a coupled set of second-order differential equations. Solving these by hand is difficult. We organize this complexity into the standard second-order configuration matrix form. This architecture organizes physical properties into three distinct blocks: the mass matrix M, damping matrix C, and stiffness matrix K. Organizing algebraic terms into a matrix structure is a necessary step to make the physical system digestible for computational solvers. But we face a computational limitation. Modern control algorithms are designed for systems broken down into first-order differential equations, rather than second-order matrices. We solve this using state variables. By defining new variables, such as making velocity the explicit derivative of position, we lower the mathematical order of the equations. This yields the target architecture, the state space representation. The A matrix is the system matrix, storing the intrinsic mass, damping, and stiffness ratios that dictate unforced behavior. Alongside it is the B matrix, the input matrix, defining how external actuators inject energy into the system. We pair this with the output equation. The C matrix mathematically maps those internal, invisible state variables to the actual physical sensor outputs we measure. The state space model compresses complex, coupled physical realities into a standardized, machine-readable format. We have transitioned from physical metal to the geometric map of the free body diagram, and finally to the digital abstraction of the state space matrix. Deriving an accurate mathematical model is the most important part of the entire control engineering process. With the physical reality now captured in mathematics, engineers can begin designing the control schemes that will direct the machine's behavior.